Hello, everybody. We finally are ready to study what we set out to do is the complexity of algorithms. So I remind you a little bit the order, the sequence in which we have done things. First, we talked about algorithms, what they are and how they are essential part of mathematics, especially of applied mathematics, computer science, where we try to solve problems and in not a way by just trial and error, but in a systematic way, which is exactly the concept of an algorithm. But it has to be carried out so that that we know that in any circumstances, no matter what input you give, you always get an output within a finite time of calculation. In other words, there's only finite many steps that the algorithm is going to use. That is by definition of algorithm. Otherwise, we have something that is not an algorithm, or what people call a bad algorithm, about an algorithm that is defective. So, but there's a big but here. Is okay. All these algorithms that we described have this property, and we will see many more. But there is a little bit of the issue now, or the second issue is how fast are these algorithms, and it's not so much about okay, you have a little problem with 10 input size, a number of the order of magnitude 1,000. How many calculations does it do before it gives an answer? Or you have a list consisting of 1,000 elements. When the numbers are small, because our computers nowadays are so fast, it doesn't really matter. However, as our technology advances, so does our social network and virtual networks, and everything is, the world is expanded enormously. Not just that there are more people than there were a century ago, the people that are now on this world and a century ago are much more connected, and there's much more information. And so all this has to be handled by computers. And so it becomes really an issue. Can we do, although we have an algorithm, how efficient is the algorithm? Now, in the older days, one really talked about time constraints. How fast could one do calculations? And to just give you an idea how this is important, when in the 60s they sent rockets to the moon, these are very delicate operations, and if you are trying to land a module on the moon, you cannot be off by more than a couple of centimeters in where you intend to, when you originally launch your trajectory down to the moon surface, because you might completely miss the moon if you even off with a little degree off. On long distances, these degrees or these little mistakes make huge differences. So what needed to do was constantly adjust, because of course you cannot have it perfect. So constantly the module would get closer, and then calculations had to be done and see, oh, we're not going right. We have to do a little bit. This thruster had to have a bit more juice in it, and the other one should shut down a little bit, and constantly we had to calculate. This is so-called real-time calculations. But these calculations are not trivial. There's a lot of parameters that had to go into this. It are very complex systems, such as landing a moon module for the first time on a place with nobody on the ground to tell you what's going to come there, with transmissions that have a lag. That's another thing. There was a lag because a couple of seconds, but there was a lag because of the distance, right? We know that there is no immediate transmission of sound or radio waves or light. There is a time it takes, and the farther away it takes, the farther away you are, the longer it takes. So for the moon, it was not that far in astronomical terms that it was a major thing, but it was there, and all these things had to be calculated, but I had to take into calculation. So NASA used, of course, computers. Computers existed already there, not the PCs. PCs were something that was still more of a dream for all these people in their basements, like Steve Jobs and all this. But the computers were there. I'm not saying there were already some forms of PCs, but not the modern PCs that we know, or the calculations that we can do with our cell phones. No? But they had huge computers, which were based on with transistors, were very hard to keep them running. They would heat up because this electricity goes through these transistors. They were huge, as I said. They were in the basement of the. I forget now exactly whether they are at Cape Canaveral or somewhere around there. I don't exactly know the details of that. I'm sure you can find a YouTube movie on the history of NASA, but they were huge, and they were. And just to do all the calculations, they needed an enormous amount of computers to do all these. They would put them, of course, parallel. Each would calculate a little thing like what does this thruster have to do? What does this thruster have to do? What is this sensor has to do? What is this sensor measuring? What do we can conclude from this? What are the mistakes, the errors that we can expect? All these calculations had to be done, but this huge room. You can see pictures of it. And as I said, the power of those computers altogether is basically what our laptops and iPads nowadays have. It's amazing how much we have been able to simplify this technology. So time was very much of an essence, but nowadays we have greatly improved our computers, and so time is still of an essence, but it is a harder thing to measure because we have very many different types of computers. Your iPhone or your smartphone or your tablet or your desktop or laptop computers have a certain speed. They're already quite fast, as I said, compared to the 60s. It's amazing. They also have much more memory. That's another thing. That another problem that one had to face was not just the time that it took to do calculations, but also the amount of memory that you had to store, and especially because memory storage also is time consuming because you have to access the memory, you have to store it somewhere, and then have to access it. That all these problems are serious problems. Now we are not talking about that. This is not computer science or computer technology courses, but if you're not aware of it, but I'm sure many of you are aware of it, that is a major issue, all these things. But now we have also different computers. There are computers, servers that are much more faster. I mean, there are professional computers that you can buy for $10,000 instead of $1,000 for a regular desktop, which are much faster. And then there are the so-called supercomputers that are way much faster. So we have different types of computers. So nowadays, to talk about time it takes to calculate is a little bit misleading because which computer are you talking about? Are you talking about our supercomputers, which, of course, for certain problems we want to use these supercomputers, but not for everything. If we have to encrypt our we'll talk a lot about cryptography. Remember, this will lead to complexity of algorithms will eventually lead to cryptography, which we will get to, but a little bit later in the course, because we will have to do other things. And cryptography is based on the fact that certain things are still hard to take still a lot of time to calculate. We'll talk about that later. But the issue is that we need to implement it, and even that needs we need computers to do this that are fast enough to be able to carry it out, and not a supercomputer. I don't want to do pay my go through online banking or pay something online and have to wait for a supercomputer to come and tell me, okay, yeah, come, give me your credit card, I'll take care of it. You have to do it. The computer itself that you're working on is going to do this. So, in other words, I'm saying this to tell you that we need to think not about the fastest computer that we have, but the normal computers that we have. So time, therefore, is a little bit misleading. So nowadays, one often just says the number of steps, basic steps. Now, that is still vague. What is a basic step? Depends a little bit on how deep you want to go into your computer. For us, for instance, the basic steps, so what we call basic steps will be addition, which is not entirely true. Addition of integers, but sometimes we even do addition of real numbers, but that's already much harder. So a lot of problems I'm hiding here under the carpet, because after all, this is a field. The complexity theory is a huge industry, if you want. There's a lot of scholarship about it, so a lot of things to deal about it. But so addition, multiplication of integers, but real numbers it gets trickier. Or we have talked about actually multiplication, not seeing it as a basic step, but thinking of it multiplying binary numbers, and then use. Oh no, that's something that we'll do in we will go deeper into this thing in discrete math too. But for us now, multiplication, we think that's a single step. Comparisons. So is A bigger than B, or is this number equal to 7? That's what I mean, comparison. So in addition of integers, it's also the counters. How counters work, we add to a counter that's considered as a single step to go from, if I goes from 1 to n, each time that I increments, that's considered a step. So these are steps. And so what we're going to calculate eventually is how many basic steps are we doing. Addition of multiplication, comparison. There was one more that came, but it escaped me now. When we discuss algorithms, we will we'll get to I will tell you these are the basic steps. And so what we want to do is the complexity. So what does that mean? The complexity, that is the expected number of steps to carry out the algorithm. Now I'm saying expected. Let me perhaps even not say that. Just the number of complexity is the number of steps to carry out an algorithm. The complexity, that's what the complexity of an algorithm is. No, I don't know why I put this parenthesis. So let me get rid of the expected. There is a little bit, one can say something about this. And we will talk a little bit about worst case scenario, average case scenario, but for us it's basically the number of steps to carry out an algorithm, but not really the big O of that. Because if you have to, if it takes, say, one algorithm 1 takes 3n plus 5 steps, and algorithm 2 takes 2n plus 1,000 steps, then they are different. No, they are different complexities. As you just think of it as the number of steps, they are different, and depending on what the value of n is, and depending on the value of n, which do you think is going to be biggest? Eventually, this is going to be bigger, right? Of course, for small numbers of n, this is going to be a big number. Like n is 2, then this is 1004, where this is only 17. But for n is 1000, then this is 3005, and this is 3000. So for n 1000, this becomes smaller. However, when we're talking, say, a billion, then this is 3 billion and this is 2 billion and well, a little bit of change here, but we don't even talk and mention that anymore. Now, 2 billion and 3 billion, it sounds a lot difference, it's 1 billion difference, but if you have to compare this with, say, so now this is, so algorithm 1 and algorithm 2. Now, suppose we have algorithm 3, and that one takes n squared plus 2 steps, okay? Or an algorithm 4, let's say, takes 2n squared plus, let's do this 2000 here, and 2n squared plus n plus 5 steps. Okay, I'm just thinking about possibilities here. I don't know there is an algorithm that has this property, but I'm just imagining it. So let's now think about this here. Okay, again, this for small n's is smaller than this one. Bigger than this one. Sorry, now I put it in the other order, but that doesn't matter. But for when n gets bigger and bigger, then actually this is going to be slightly bigger, like say 1,000, and this is 1,000,000, and this is 2,000,000, right? But remember, for 1,000, this was 3,000, this was 2,000. So comparatively, these two are much smaller than these two. And let's put in 1,000,000. This is 3,000,000. If n is 1,000,000, then this is 3,000,000. This is 2,000,000. This is 1,000,000,000, which is 1,000 billion, is a trillion. Yeah, sorry. There are different ways of saying these huge numbers, and the so-called European French system, and there is the American system, and when it gets to huge numbers, people don't even actually exactly know anymore. But So it's a trillion. For those that are a billion, it could mean something else, but okay, let's call this a trillion. A million times a million is a trillion. So this is a trillion, and this is 2 trillions. Now, okay, this true is bigger, but relatively speaking, these two are kind of the same as these two. And that's exactly, remember, where our ON comes from. The O says, okay, it's the leading term that counts, so there's a linear term, and the coefficient in front of it doesn't count. So this is O of n. Here we have quadratics, that's the leading term, is a quadratic, and again, whether there's a 2 in front of it or a 2000 added here, it doesn't make a difference. And so this is a kind of division line that we're really interested in between ON square. Now we know that for huge n, and you have to imagine that we have to do this for huge n, okay, big n, let's call it big. It depends on what you call huge. A million is huge in some respect, in another respect it is not that huge. But so we always, whereas I should say this as a warning, caution, like all the examples you will see will be small, and therefore it's kind of silly to talk about the complexity because it's so small, right? Just keep that in mind. But that's because we can I cannot sit here and do a million calculations for you. Well, we could use computers, we could write programs to do this, but as I have announced before, is I will not do this in this course. In this course, we do not actually do programming implementation. So we will not actually see things at work. I defer that to your computer science courses that you probably also will take. Okay, so coming back. That's why we take the big O here, and okay, guys, give me 1 sec. I'm taping something. I'm taping something. Yeah, I'm recording. Yeah, tell me. Yeah, yeah, yeah. It's okay. You okay? Sorry for that. Okay, so let's go to an example. I'm going to start with very primitive algorithms. So the first one is procedure silly sum. And the input is going to be just an integer n. And so what I'm saying is, okay, I'm going to write it down for you. For I going from 1 to n, and then for j going from 1 to n. Oh, sorry, and let me call here, I'm going to declare a new variable, sum is 0. And then I'm going to say here, sum is sum plus j. Okay, let's look at an example of this kind. And I'm going to play with this example. So I'm going to start moving things around. And in fact, let me do this first. So the way I wrote it is kind of not, okay, sure, there has to be a return, right? So return sum. So what is happening? Let's try to figure out what this algorithm does. Well, we start with 0, and then we go from 1 to n. So we loop from 1 to n. And then inside that loop, we loop again from j to 1. And inside that loop, we do this calculation here. So we're taking a sum, we declare sum is sum plus j. So let's see what is a basic step. So this would be one basic step, right? Because we are adding something. Remember, addition was considered a basic step. So imagine you're somewhere down the line and doing this, and so what happens? So you have a certain value for I, say I is 3, j is 5 at this point, and your sum is a certain value at that point, and now you add j, which was 5, to it, so you get a new value for sum. What is happening next? Next, this is looping back to your in your inside loop and says, okay, increment by 1. So in other words, and we keep doing this until we reach n. So each increment we consider as a basic step. How many times will this happen? Well, it starts at 1, we will carry this out once. Then for j is 2, we'll carry it out another times. So in altogether, you see that, so this just single thing is one basic step. To carry out this single loop here, we have to do this n times this basic step. So n times this basic step. So, okay, I'm sorry. Allow me to put in a second thing here. Let me, sum is sum plus j, and sum is 0. I'm going to put here an track is also 0, and do track is I plus j. Okay, so what is changed now is that in this case I not do this addition, and then I do this addition, and so this has now become two basic steps. But we doing this still n times, right? Nothing else has changed in the sense that I loop to this n times. So what is now the number of steps I have to do? Well, now I have 2n, right? These two basic steps have to be carried out n times. Now this is the let me put things in boxes. So this is 2 times, we carry this out. Then come on. This one is carried out in 2n steps, but there's still another loop going on. Let me put this in a different color. This loop. So how many times is this carried out? Well, again, if the inside the orange box has been finished, its calculation, the loop has finished, what happens then? The program says, okay, this is finished, I'm done with this thing. Then it gives control to this loop and says, oh, the loop says, hey, I have to increase myself by 1. Just I keeps increasing. So how many times are we carrying out? This is again n times. So this inside box here, this orange box will carry it out n times. And it itself was already 2n time. It already was 2n steps. So n times 2n steps. So this would be, so the complexity of this guy, allow me to write it here, is n times 2n. So I repeat, n times because we loop n times here, 2n because this takes 2n steps. Okay? So this is the complexity of the purple box. Now, there are 2 more things here. We had to do these 2 guys things. So we could say that the complexity here in the number of basic steps is 2n squared, this number, plus these 2 initial steps that we had to do. Okay? But it doesn't, we are not really interested in that. We need in the complexity. So this is the, let's say, literal complexity. But nowadays, when we say complexity, we mean the big O. The book says big theta. I have told you we not make a distinction between big theta and big O. It's a theoretical distinction that most people don't care about. So I'm just going to say this is big O of n squared. So this program takes big O of n squared times to be carried out. Okay? So let's play a little bit with this. I hope that I can do this without erasing too much. So I'm going to get rid of all my outside commentary here. And what I want to do now is change this slightly. And you'll see what I mean with slightly. Okay, nothing changed. Okay. So what I'm going to do is, let's do this. Let's first start with this one here. I'm going to move it here. So what has happened now? Let's think about what is going on in this calculation. I hope you still agree that this took 2n steps. The whole thing, I moved the whole thing, so the loop itself has not changed complexity. So what is now the deal? Sorry, let me erase everything that you don't get confused with what I have here. So at the moment we have now a different complexity. This is a new program, silly sum, different silly sum, okay? And what's the complexity of this one? So when this box, there was an orange box, right? But let me not do this anymore. So when this thing was carried out, 2n steps were carried out. What about the first loop? Let's think about how the program does. So the program starts as sum is 0, track is 0. Okay, then for I going 1 to n, do, what is it doing? Everything that is indented here, well, that is nothing. So what is this loop doing? It's just sillily incrementing I from 1 to 2 to 3 to 4 to 5 until it reaches n. So how many steps is this? N steps. Because it doesn't do anything except incrementing itself. Okay? So, what is that now? After it's done this, it starts carrying out this calculation. By the way, what's the value of I at that point? Honestly, I am not entirely sure. I think it's n, but it could be n plus 1. I don't exactly know what the intent is of the pseudocode when you jump out of a loop. What has happened to the value of your counter? So up to that doesn't really matter really. But the point is, it carries out first this, and when it's done with that, it carries out this. So now we don't have to multiply these things, we edit them. It's 2n plus n, and then of course, don't forget we have 2 steps here, so plus 2. So this is actually 3n plus 2, so the complexity of this thing is O of n. You see how this makes a difference whether you indent, because that means inside, and not. And this is very typical for loops. Loops have this contribution. Each time you loop, you're going to have, you have to do this n times, assuming that the loops have a fixed, some loops are fixed. So let's compare this now with the following program. I'm sorry, I keep doing this on the same one. So here's my CD sum 3 if you want. So, okay, let's do this away. Let's do this away. So I'm going to make the following adjustment. I'm going to get it back to the original one. So I'll get this back inside. So we really want to do this, right? Otherwise it was a bit silly what we were doing. But I'm going to change things. I'm going to say, I'm going to change this into 5. Okay, so since I have not changed anything in the inside, the complexity of that loop is still 2n steps. Okay, you could debate here a little bit. Okay, perhaps you might argue and say, Professor, didn't you say that addition and comparison? Oh, okay, now I know what the other one was. Assignment. That also considered as to be, or declaration is also considered a single step. That's what, sorry, that's why I counted this as a single step and this as a single step. Sorry, I hope that was clear. Now you could say, Professor, didn't you say that increasing a counter also counts for a basic step? Yes, true. It's a one more operation that has to do. So you could, some people might argue, say this is 3n instead of 2n steps, because you also have to increase your counter each time. Why do we not care about that? Remember, we take the big O. Whether this is 2n or 3n in the big O calculation, it doesn't matter anymore. That is exactly why you use the big O, that you don't have to really calculate every single step that you do. And to be truthful, that really depends also, the number of steps that you do also depends on the implementation in which language you implement this, because some languages require you to do some more steps, or other languages would say, I don't have a primitive operation that is multiplication, you have to tell me how to multiply. So that becomes also something that has a complexity. So when we say basic steps, we think in terms of what the computer already knows and can do in a blink of an eye, so to speak. And we don't want to look into into the guts. We don't want to open up the bolt, nuts and bolts of this thing. These are basic steps. And by the way, there was a program in the old days called BASIC, because it was exactly consistent what was at that time thought of basic steps. But okay, not that, but it still had loops, so it was a bit, it's not really true either. Okay, but what has changed now? Sorry, this is the whole thing. How many times are we carrying out this inside part here? So how many times are we, this inside part itself is 2n times, but how many times carry we it out? 5 times. So we get here 5 times 2 to the n, that is 10 to the n. So notice that the complexity now is O of n. Let me write it there instead of here. Okay, so the complexity changes really. Oh, you cannot just say, oh, because we have a loop, it means it increases the complexity. Not necessarily. Because if this loop is like of a fixed, especially because the loop here is a fixed endpoint, so it's a fixed length, it doesn't depend on n. So you see how subtle all these things are when we need to calculate this. Okay, so I want to do 2 examples, and then we're going to stop, and we continue. We're going to take our time for this, because this is not so easy anymore, but let's look at some of the samples that we already did of algorithms we did, and try to figure out what their complexity is. So we had to, I'm going to copy this one. This was the procedure that the very first algorithm that we discussed was max. And max had a list of integers or real numbers, I don't know, okay, let's call them integers. So these were integers. I'm just taking the form that the book gives, but again, we could also take real numbers here, but with the proviso that adding two real numbers is considered a basic step, which it isn't, I should say, because storing a real number is a very cumbersome thing. Real numbers have infinitesimal expansion, so you're actually not storing a real number. But okay, let's not get into the nitty-gritty of this part. So what do we do then? How did you calculate the max? It was very simple. You say, I'm going to go to the list. If I find a number that's bigger, I'm going to say that's the new maximum. So the original maximum would be the first element. So max is A1. And if there is no more in the list, that's the end of it. But I know now I'm going to loop. So the next thing is I'm going to loop for I. Now we have to loop. What we're going to do is we're going to look at the next element and the next and the next. So we actually start from 2. So for I going from 2 to n, what will we do is we do a comparison. And if the maximum that we have, our current, what we think is a maximum, but if that is smaller than the new one, remember, the counter is the index of the element in the list. It's the position of the element in the list, so AI. If that is smaller, what we thought was a maximum is actually smaller than an element in the list, well, then it's not a maximum, it's that new element that should be then the maximum, at least so far. So max is then AI. And then we, at the end, that's it. Sorry. Return max. Okay, so let's analyze the complexity. We have a little less space there, so I'm going to do it on this side here. So this is one basic step. It's a declaration. It's an assignment. So it's one basic step. Let's look at we have a loop, but it's like many things have to be analyzed from the inside out. So we dive into the loop and see what's going on in the loop, and if there's another loop, we dive into it until we are on in the core of the problem, so to speak. What is the core step? The core thing that is being carried out is this comparison. So a comparison, remember, was one step, if, and once it does a comparison, so it had to do one step, and then it might have to do nothing, but it might also have to do something. And this is what we normally call the worst case scenario. We always have to assume that the worst case can happen, that an action has to, if it's possible that an action needs to be taken, that action will be taken. We just are going to assume that, because we cannot in advance predict whether this, if I would give you a list in which the numbers are always going bigger and bigger, then we constantly going to have to change the numbers, right? If these are increasing numbers, or if the list is already sorted, then this number will constantly change. So we constantly will carry this out. So that, in some sense, although this, if we would know it was sorted, we would have the answer in a blink of an eye. We just say the last element. But if we don't know it's sorted, it becomes the worst case scenario. And so this is exactly also an example of how sensitive an input is to an algorithm. The algorithms are designed for certain inputs or work well with certain inputs and not so well with other type of inputs. And so that's also why we have sometimes many algorithms to kind of solve the same type of problem, because the inputs have different features that makes it worse or better. Coming back. So worst case, and that's why we have the counters. I'm not going to use the word worst case. I'm just going to say the number of basic steps is one comparison and one assignment, so 2 steps. So this is 2. Now this is inside a loop. Okay, so this is inside the loop. So let me color the loop again. This is the loop. So this box, how many times is this box carried out? Let me put this on this side here. Well, the counter goes from 2 to n. So actually it only counts n minus 1 times. The counter will change n minus 1 times, and each of these n minus 1 times it will carry out this two-step instruction. So this two-step instruction will be carried out n minus 1 times, so the total thing here is n minus 1 times 2. Okay, so what is the complexity? So the complexity, let's write it out first without the O. That would be here, this number, 2 times n minus 1. And there was, of course, this first one that I already said, that is just plus 1. Okay, so what is this then? If we work this out, 2n minus 2 plus 1, so this is actually 2n minus 1. But that's not really how we see it. What we see is the O of this complexity, and that is just O of n. So notice, for instance, you might say, oh, I was so smart that I started from 2 and not from 1, because if I start from 1, I know that this is not going to happen, because that's A1 is A1, right? So I was smart, I started from 2. Yeah, you were smart, but in the O end it makes a difference too. Whether you have n minus 1 or n here, eventually that would make no difference, right? So it shows you, and this complexity is somehow humbling, that certain things that we think are very smart and ingenious ways of making it quicker actually do not bear that much on the problem. And it's only when now that we know what complexity is, and then we can talk about it. I mean, I'm talking now the history of this science, is that we more and more are aware that, and especially because our computers are so fast, that it might be sometimes better to make it work a little bit more, but if it's low complexity, it doesn't matter, at the cost of making our programs much more legible, right? Because in the older days, you saw programs where one looked at special cases because special cases were faster. And true, at that time it might have been needed to do that. But nowadays, if you say, okay, whether I do this special case, okay, it's going to save me half the time. But what is half the time here? We're now not talking about minutes, hours. We're talking about nanoseconds. Half a nanosecond, I'm sorry, but I don't care about that improvement, because that's how fast computers are. Okay, that's the idea. I should not diminish the fact that our people are really trying to improve algorithms, because even small minor changes could be important. The difference between being able to and not able to calculate something, that's a different thing. That's where people are, this kind of research happens at the edge somehow, where things are about feasible and yet not feasible anymore. And so by improving your algorithm, you can actually make something that was originally not feasible. But that's it's tiny improvements. This is a much larger scale. We will talk about it in the next lectures, or perhaps one more lecture, 2 lectures from now. I'm going to do one more example and then we will stop. We have also seen the linear search. So the linear search. And again, I'm going to just copy the program as it was given. Yeah, and I think I gave a different algorithm, but this time I'm going to just take the one that the book proposes. I don't think they're different in complexity. No, I'm pretty sure they are not. No, I'm 100% sure they are not. But it is just so x is an integer, and then a1 up to an is a list of integers. And they are called distinct integers, so that the search. And so the whole purpose, remember, is to find where is x in this list. Well, it could be not there, and if it's not there, we put location equal to 0. If it's there, we let location be what we think the position it is. Okay. So how does it go? According to the book, what they do is they start they kind of manipulate the counter in a different way. They don't do a for loop. They say, okay, the counter is 1, and then while while I is less than n, and two conditions, and x is not equal to ai. So what does this mean? While we are, this first part tells me I'm looking in the list, because once I is bigger than the list, there are nothing left anymore, right? So I should not look, I should only be looking for an I less than n. So this is a condition that has to happen. If it doesn't happen, then stop. Okay, so this is that. What does this do? It says, well, I'm looking for this guy, and when I don't find it, well, I go to the next one. So that's exactly carried out by incrementing the counter by 1. This is going to the next one. Okay, you could do this with a if then else perhaps, but this is the way that the book proposes it, and then it says, okay, if now it's flush on this. Oh, okay, yeah, it's flush with while, right? So if then let me write this, otherwise I have to change. So if I is less than n, in other words, if you loop, if what are the two ways to jump out of this while loop? Is either because your I is too big, or you have found equality. And if you found equality, then you can stop. So in other words, if you were still looking for inside the list, then the equality, if you're inside the list, then the AI that you found is X. So then the location is I. But if that's not the case, else, then the reason you're no longer in the list is because although this condition always was true, this condition fails, and that means that I is now n plus 1, actually. But that means that the x was not in the list, and according to our design, this should mean we should put location equal to 0, and then again we do return location. Okay, let's calculate the complexity. This is again a single assignment, so 1. So we have a loop here. This is a type, whiles are a type of loops, right? The difference with a while loop as opposed to a for loop is that we don't exactly know how long the loop is going to last. So we have to analyze a little bit what happens, but we also have to always think in the worst case scenario, right? So this will be carried out, but notice these are actually two instructions now. We have to do a comparison and another comparison, two comparisons. So actually each time the while loop is carried out, this will be 2 steps. Okay, and if you actually, sorry, each time you will want to start the while loop, it requires 2 steps. But again, that's not really that makes no difference when it comes to complexity. So it is well within your, it's well accepted that to consider this one basic step. So in other words, this Boolean combination here of 2 steps combined in 1 step, that is allowed because complexity, remember, does not care about these factors, these constant factors. This is whether this is twice this or once this. It's, as far as complexity concerned, the same. So I'm going to pretend this is a single basic step each time the while is carried out, and then this, of course, is also a single step. So how many times now is this while loop carried out? This is now a little bit of the issue. Well, let's look at the worst case scenario. And in this case, okay, this is a good question. Worst case scenario is a vague term. What is this in this case? When is the algorithm have to run at the longest? When x is not in the list. So how many times will we carry out a while? Well, we'll go through the whole list. So the worst case is that we have to do n times this list. And each time we do this one basic step, so it's when n times 1. So the total number of basic steps within this... no. Sorry. Let me do the coloring then, because then it's see it better. So this is the loop, right? This part is only this part is the loop. So this will be n. What happens with the if? The if, notice, is flush. It's not carried out in the loop. So it is carried out how many times? Well, only once, because there's no loop anymore. So what is the deal? Well, we have to do one comparison and one assignment. So and then another assignment, then or else. So it's either this one or that one. So in either case, we do 1 plus 1, so 2 basic steps. So if we write this all down, we have 1 plus n plus 2, which is n plus 3. So if we take the O, it's just O of n. So this is what we will call this linear, and that's why perhaps it's also it's not why it's called linear search, but it's the complexity is linear. But we talk about different complexities later. Okay, so this is the linear search. I'm gonna give you some homeworks of the basic guys that we have done, or simple programs, and you try to now figure out by yourself what is the complexity. And then we go to a little bit more advanced procedures, algorithms, and see what their complexity is, and then we will finally talk about differences in what is feasible complexities and what are considered unfeasible complexities. All right.